All right, let's do. We're going to look at quiz 12 here. Wow. Oh, this doesn't even work. Microphone worked before. Screen's now, the screen didn't fire up. Now the screen fired up. Now the microphone just doesn't seem to work. Oh, battery's dead. We'll see what we can do. All right, we're looking at 12. So we want to calculate a empirical formula here. So we want to take this 4.722 grams of CO2 and we need to get grams of carbon out of this. So we know that CO2 from our previous problem is 27.29% carbon. So at 27.29% carbon, we can take 0.2729 times that, and we can get our grams of CO2. And that, or excuse me, grams of carbon in the compound. That carbon is right here. So how many grams of carbon do I get out of this? Somebody tell me the answer. What do you got? How much? 1.39 grams of carbon in that? 289. 289.289 grams of carbon. All right, and then the percent hydrogen in water is 11.19%. So if I take 0.1119 times 1.289, I'm going to get how many grams of hydrogen? How many grams of hydrogen? Somebody yell it out. How many grams of hydrogen? .1442 grams of hydrogen. Then I can take where my hydrogen comes from right here. Now, for my grams of oxygen, that is going to equal to 3.150 minus 1.289 minus 0.1442. It would be nice if there's an extra battery in here. It's actually a good battery. Okay, so with that now, how many grams of oxygen? How many grams of oxygen? How many grams of oxygen? How much? All right. Now convert all those to moles, divide by the smallest, right? Convert all those to moles, divide by the smallest. 9 and 11. All right, 9. For number 9, this is for sure a limiting problem. And we've got 100 grams here. We've got 50 grams here. We are going to figure out our moles of phosphorus trifluoride that we have. And that, of course, is going to come from there. Then our mole factor fraction is 1/2. That's how many moles we need. And you're going to figure out how many moles you have by taking the 50 grams to moles. And then you're able to figure out which one's limiting. And then we could get, the only thing we need is the moles of PF5. We need this right here. So we're going to come off of what we have of the limiting to figure out the moles here. Which one's limiting here? Is it PF3 limiting or XEF4? Somebody tell me which one's limiting. XEF4 is limiting? Okay, so we're going to be coming off of here. Once you figure that moles out, and then the mole factor fraction is 2/1. And 9 and 11. We already did. We do 11. We did 11 previously. Okay, let's go to our guide here, see where we're at. We left off doing molarity, right? We did some molarity. Third battery. I was working. Oh, that's much better. I'm not to leave on it. Plus, it'll come through for the recording directly through. So, all right. So we left off. We talked about molarity here. Remember now, molarity is moles in solution, but in order to get moles in solution, we're dissolving grams, right? So we're going to do some stoichiometry problems that involve molarity. And when we do that, really, we're talking about dissolved grams. The problems are easier because we don't have to deal with grams in order to get moles. All right, let's do some molarity examples here at the top of page 9. So it says it wants 0.250 liters of solution of 5.3 molarity NaCl contains how many grams of NaCl? Now, we're not going to memorize this stuff. I call this a double unit number. This is like MPH, which stands for miles per hour. That's a double unit number, right? But we can just put MPH. This right here means you have 5.30 mole of NaCl per liter of solution. Now that I wrote that there, it actually looks nice. I'm going to start with my single unit number. You always start with a single unit number. If you've got a single unit number and liters is a single unit number, you always start with that and see if you can leave the double unit number alone or flip it. So in order to get grams, I need moles. So I'm going to leave this. I wrote it down here. I like it. Just like this, because when I start with my single unit number, my liters of solution is going to cancel out, right? So I'm going to start with my single unit number, 0.250 liters of solution. My liters of solution is going to cancel out. And I'm going to add one step here because I have moles, and I'm going to go 1 mole of NaCl is grams of NaCl. 1 mole to grams. And an Na and a Cl should get us 58.04. 58.04. Moles cancel out. And that should get us to 3 sig figs, 3 sig figs, 3 sig figs, 4 sig figs. 76.9 grams of NaCl. The next problem is pretty much exactly the same thing. I need to do a better example. This is 0.325 liters, right? 325 milliliters, 0.325 liters. So I'm going to start with 0.325 liters of solution. I know that this is moles over liters. I'm going to bring this down as is. I'm not going to flip it. So let's put this in as 0.000823 mole of Ki per liter of solution. Then we'd simply go 1 mole of Ki to grams of Ki, right? And this would be grams 166.00. So liters cancel out, moles cancel out. And if we run this through our calculator, just going to multiply everything on top. 3 sig figs, 3 sig figs. My answer comes out to be 0.00444. Is that right? Grams of Ki. Now I still have students thinking this is 5 sig figs. This is 3 sig figs, right? Because if you put this in scientific notation, you'd call these 2 zeros junk, right? You'd just skip it. 4.44 times 10 to the minus 3 would also work. Okay, let's do this next example here. We've got 25.3 grams of sodium carbonate. Dissolved in enough water to make 250 milliliters of solution. This decimal point is there to make this be 3 sig figs, right? Without the decimal point, this is 2 sig figs, right? What is the concentration of sodium carbonate? What is the concentration of Na plus and CO3 2 minus ions? Well, first off, we know that sodium carbonate is soluble, aqueous, right, in solution. When this splits up, get 2 sodiums. Two sodiums. Now, I'm still seeing people write ions as Na2 down there with a plus. There is no such ion. You'll never find that ion on the pink sheet. The CO3 stays together. CO3 2 minus. Okay, let's calculate out. We need the concentration. We need the molarity of this. So if we need the concentration, we need moles over liters. It should put, we need molarity here. So we need moles over liters. Doesn't matter how ugly it looks, just get moles over liters. Let's start with the grams because that's going to get us the moles, right? So we are going to start with 25.3 grams of Na2CO3, sodium carbonate. And let's see, how many grams in 1 mole? 1 mole sodium carbonate. How many grams? $105.99. Okay, 105.99 grams cancel out here. Now I need moles per liter of solution. 150 milliliters. Nice. We're not going to memorize any formulas. Here's what we're going to do. We're going to take this 250 milliliters and draw a line right here because we need moles over liters. So I'm going to put it down below. I have moles in the numerator. Yes. Let's take this 250 milliliters right here. Put it in the denominator. And I'm going to change that 250 milliliters to how many liters? 0.250 liters. So 0.250 liters of solution. I have moles over liters. Grab your calculator, punch that pig in. And I think we're going to get 0.955. Okay, so we have 0.955 molarity. Sodium carbonate. When this splits up, we get one carbonate. So this would also equal my carbonate ion. But my sodium, I get 2, right? So my sodium concentration is going to be 2 times 0.955. So my sodium ion is going to be 1.91 molarity. Okay. Now, the next type of problems with molarity is called dilution. And this can work if you have a higher concentration solution. You just add water to it, right? Now, in lab, you cooked off the water, if you will. You made it more concentrated if you've done this week's lab already. So there is a way you would have to evaporate off the water to make it more concentrated. But typically for a dilution problem, you take your more concentrated solution and you add water to it. So it works pretty easily. This equation right here is what we'll use. And this is really pretty much simple, just the way it looks. It's molarity of the concentrated times the volume of the concentrated equals molarity of the dilute times the volume of the dilute. Just got to identify which one. So here's, for example, we have 0.850 liters of a 5 molarity copper nitrate. It's diluted to 1.8 liters. What is the molarity of the dilute? So we are looking for the molarity of the dilute. This right here is the volume of the dilute. This right here has to be the molarity of the concentrated. And this has to be the volume of the concentrated, right? So we can just put them in to this molarity of the concentrated times the volume of the concentrated, these two here. So we've got 5 molarity times 0.850 liters. Area of the concentrated, volume of the concentrated equals molarity of the dilute, which is what we're looking for. Volume of the dilute is 1.80 liters. So multiply the 2 on the left, divide by 1.8 liters, right? Your liters are going to cancel out. You know the units are going to cancel out. Nice. We're just solving this for the molarity of the dilute. And my molarity of the dilute is 0.36. Okay, so my molarity of the dilute is equal to 2.36. What volume of 1.59 molarity KOH is required to prepare 5 liters of 0.1 molarity? So you could just look at these. This is the molarity more concentrated, right? This is concentrated. This is 1.59 versus 0.1. So then I know that this right here is the molarity of my concentrated. This is the molarity of my dilute. This is the volume of my dilute. I'm looking for the volume of concentrated, right? I'm going to put this in the same way here with this equation. The molarity of my concentrated is 1.59. I'm looking for my volume, my concentrated. Molarity of my dilute is 1. Volume is 5. And then my units are going to cancel out. Molarity cancels out. My volume of my concentrated is 0.314 liters. So I take 0.314 liters. I would add water to 5 liters, right? Just add water to 5 liters. All right. We're going to do a little pH. Make sure you can run your calculators. Please run your calculators on everything we do now. Don't sit there and wait for somebody to do it, because I want to make sure you're running your calculator right. So we're going to do section 4.6 pH. The concept of pH was first introduced by a Danish chemist. And then in 1909, it was revised to the modern pH in 1924. And I have students ask me, well, what exactly does pH stand for? So I looked it up, and where did I go? Wikipedia. Because every time I looked it up, it was a different answer, and it still seems to be a different answer. I always thought it was potential hydrogen, but power of hydrogen. We really don't know. We don't know why the subscript is there. It's kind of weird. But pH is a logarithmic scale. So let's review logarithms, everybody's favorite. But it is a logarithmic scale. If I take the log base 10 of 100, what answer do I get? Grab your calculator. What is the log of 100? Got it in, I hope. The answer is 2. What the heck does that mean? That means this. It's returning the exponent. 10 to what number gives us 100? base 10. 10 to what number gives us 100? And the answer is 2, right? So anytime I did logarithms in math, this is exactly what I did so that I could duplicate everything. Because you know what those sucking math teachers do? They turn around and change the base on you, right? Immediately, they turn around and change the base on you. But that didn't fool me because I just matched this up. And then they'll say, okay, class, now we're in log base 2 for whatever reason. Log base 2 to the 8 equals what? 2 to what power gives me 8? 3, right? That's what they turn around and do. Now, log base 10 of 1,000. We don't need a calculator now. We do not need a calculator. 10 to what gets us 1,000? 3, right? 3. But here's my point. This is what a logarithmic scale does. This number here is 10 times higher, correct? Number here is 10 times higher. What's the pH or what's the logarithm do? Adds 1, right? So when we do pH, something can be 10 times more concentrated. Your pH is going to go up by 1. If it's 100 times more concentrated, your pH is going to go up by 2. That's what a logarithmic scale does. However, we are not going to have any numbers like this. We're going to have negative numbers. So we can have log base 10 of a number like this, 0.001. And log base 10 at 0.001 in your calculator will return an answer of -3, right? -3. Now pH equals the negative log. And if I put this number in, you're going to see it coming up, 0.001. We are always going to get a negative number when we do the logarithm. But pH has a negative right here. So really, you have minus a -3. So we end up with a +3, right? This negative here is just to make the number positive. That's why the pH is the negative log, because our value there is going to return a negative number. All right, let's go to the next page and see what we got. First of all, let me actually go to here. On page 11. So here is the pH column. And most of you know, maybe blood's going to be 7.35 to 7.45. Pure water, neutral would be my neutral here. pH should be 7. pOH would be 7. Unfortunately, stomach acid in here. Gastric juice, freshly secreted gastric juice, looks like about a 1.5. like about a 1.5. That's wicked. Vinegar, stomach acid. You maybe know some people that are popping Tums or Rolaids all the time, right? Try to cool down their stomach acid. Now, when you get down here, you get a base. Anything that's slippery is a base. So you know if you swam in the ocean, that water is a little bit more slippery than a lake or something. But you get down here, you've got bleach and sodium hydroxide and stuff. Okay, so let's calculate some pHs. Here is all of our equations. So pH, negative log of the H plus or H3O plus would be the same thing. H plus or H3O plus here again would be the same thing. So if we go back to the log of 100, that log of 100 is going to get me 2. If I wanted to get 100 back, 10 caret 2, I get my 100 back, right? So the inverse of log is to raise that number to the power of 10 to get that back. If we have an acid solution, our H plus, I think I'll use this H. We'll do H3O plus. My H3O plus, these brackets equal molarity. That's just saying my units are in molarity. My H3O plus is going to be greater than my OH minus. My pH for an acid solution, less than 7. Right? Less than 7. This is the less than left-hand alligator. Obviously, then, if I have a neutral solution, plus better equal my OH minus. And then my pH better equal 7, right? If I have a basic solution, I better have more OH minus, right? If I have a basic solution, I better have more OH minus than H3O plus. And my pH better be greater than 7, right? All right, we'll use all these on the next page. So here's all of these equations we're going to use on the next page here. Come back and do one of these problems. So let's go to the bottom page 11. At the bottom page 11, pH. This is going to be the negative log of H plus, right? negative log of H plus. That's one way to do it. The other way to do it is to take 14 minus the POH. Always two ways to get these. POH should be the negative log of OH minus. Negative log of OH minus, or 14 minus the P. Let's put that much in for now. So, well, we'll put it in. In order to get OH minus, we can take 10 raised to the negative POH. 10 raised to the negative POH. And the other way to do it is to take 1 times 10 to the minus 14 divided by the H plus concentration. 1 times 10 to the minus 14 divided by the H plus. In this column, to get our H plus or H3O plus, there's two ways to do it. 10 to the negative pH. Other way to do it is 1 times 10 to the minus 14 divided by our OH minus. There's two ways to get everything here. All right, grab your calculator. Take the negative log of 1 times 10 to the minus 3. Negative log of 1 times 10 to the minus 3. Negative log 1 times 10 to the minus 3. What do we get? We get 3, right? We get negative 3, but this negative makes it a positive 3. So we get a positive 3. The quickest way to do the POH is to take 14 minus the pH. If we take 14 minus 3, we are going to get 11. The best way to get the OH minus, there's two ways to do it, would be to take 10 to the negative POH. If we take 10 to the negative 11, we simply are going to get 1 times 10 to the minus 11. Is this an acid or a base solution? Acid or base? This is an acid because my pH is less than 7, right? My pH is less than 7. For this one, I have my concentration of OH minus. So let's get the POH this time. Take the log of this, the negative log. Negative log of OH minus will give me my POH, right? And if I take the negative log of that, I am going to get 5. Yes, 5. Then that makes my pH. These two got to add up to 14. So 14 minus my POH, 9. What do you think this number is going to be? It should be 1 times 10 to the minus 9. One times 10 to the minus 9. Now, you want to make sure that you are correct on these. If you take your H plus times your OH minus, you will always get 1 times 10 to the minus 14. And if I look at these first two columns I did, this times this, 1 times 1 is 1, 10 to the minus 3, minus 11, minus 14. When we're multiplying, we're adding exponents, right? When we're multiplying, we are adding exponents. Well, this pattern works provided this number is a perfect 1. So if this is a 6, what is this going to be? 1 times 10 to the minus 6, right? If my pH is 6, my POH here is 8. These two got to add up to 14, right? And my OH minus is going to be 1 times 10 to the minus 8. What do I have here? An acid or a base? Got a base, right? pH is greater than 7. Just looking at my pH when I do this. Here's my pH is 6. This is an acid. My pH is less than 7. My POH is 1. What's my pH? 13, right? These two are going to add up to 14. We're going to get 1 times 10 to the minus 13. And then 1 times 10 to the minus 1, right? This is a base. All right, let's change this so the numbers don't work out so easily. So we're actually using our calculators. I guess we can do this one. My pH is 7. My POH is 7. My H plus is going to be 1 times 10 to the minus 7. My OH minus is going to be 1 times 10 to the minus 7. Be neutral, right? All right, let's take the negative log of this. What's our pH? Grab your calculator. Take the negative log of this number. Negative log of this number. And if we take the negative log of that number, we get what? 4.80? 4.80? Okay, 4.80. My POH, 14 minus my pH. So 14 minus my pH would get me 9.20. There is two ways to get this. Let's go 10 to the negative pH, 10 to the negative 9.20. If you take 10 to the negative 9.20, we get 6.31 times 10 to the minus 10. If you did it the other way, it would be much more accurate. Because we're losing some numbers here. Because this 80 is rounded, which makes this rounded. This is off a little bit. So if we take 10 to the negative 9.20, we get 6.31 to the minus 10. Is this an acid or a base solution? You got acid with 4.8, right? If our OH minus, so that's a perfect number again, skip that. 3.72 here. If this is 3.72, what is my POH? $10.28, right? 14 minus 3.72 gets me 10.28. And since I have 10.28, let's do 10 to the negative 10.28, 10 to the negative 10.28. Now let's talk about that on your calculator. Depending upon what calculator you have. I have 10 to the X. So this 10 to the X is a different color. So I would have to hit second log, and that would bring up my 10 to the X. If you have this caret button like this, I would use this. If you have a TI-30XA or a TI-36, you have to put the number in first. So when you do logarithms, you have to put the number in first and then hit the button. Or if you're doing 10 to the X, you have to put the number in again, make it negative, and then hit second log. So make sure we get this in. I'm going to put it in. Make sure whatever calculator you have, it matches. And use a negative on your calculator, not a subtraction. You don't want a subtraction, make it a negative. So I'm going 10 to the negative 10.28. So make sure, grab your calculator. Oh, I put in 20.28. That is not going to work. And to the negative 10.28 gets me 5.25 to the negative 11. So we get 5.25 times 10 to the minus 11. For here, we can go 10 to the negative pH, 10 to the negative 3.72. And if we take 10 to the negative 3.72, we get 1.91 times 10 to the minus 4. Now, let me see if we're right. I'm going to take this number Let's just look at it this way. Let's just look at it this way. If I multiply, remember my H plus or my H3O plus times my OH minus concentrations, if I multiply them together, I should always get 1 times 10 to the minus 14. Always, always, always. If I multiply my two blue numbers together here, it's going to be close to 10. And if I add my exponents, negative 15, right? But what is 10 to the negative 15 is 1 to the negative 14, right? So these two numbers right here, when you multiply these two, you should get 10. When you look at the exponents, you should get a total of negative 15. And you know you've got it right. All right, let's do one more and then do some stoichiometry. If we do this 2.14, let's do this 9.88. So this would be 10 to the negative 9.88 here, right? So 10 to the negative 9.88. Negative 10. Now I'm going to calculate the OH minus using my H plus. This is going to be 1 times 10 to the minus 14 divided by that answer right there. So if I multiply those two together and I get 1 times 10 to the minus 14, I can take 1 divided by 10 to the minus 14 and divide by the other. So punch that in your calculator. Do not put in times 10. Do not put in times 10. Do not put in times 10. 1 EXP, the negative key, not the subtraction key, negative 14. Divide by 1.32 EXP, negative 10. Do that in your calculator right now. Make sure you're putting it in correctly. You should get 7.58 times 10 to the negative 5. All right. This answer right here, if we add these up to 14, what is that going to be? 4.12. So you could finish this table off. This is what Al does. You're doing some pH calculations, right? You're doing some. Now let's go back to page 10. Are our strong acids on page 10. What do we know about strong acids? Hopefully, I've said it enough. These hydrogens are going to come off at 100%, right? 100%. We have strong bases. These OH minuses are going to split up in solution. It's all about OH minus for a base. All about H plus or H3O plus for an acid. Let's do this acid one down here first. Now, this is aqueous, and this is going to split up into H plus ClO4 minus. ClO4 is perchlorate. We know there is no H. So if you have a bottle of, let's say, 1 molarity, HClO4, there isn't a single hydrogen hooked up inside that bottle. This is a strong electrolyte. It's going to split up into ions, 100%. So if this is labeled 0.0125 molarity, you get the same number here. This is 0.0125 molarity. None of this is hooked up in there. It's all split up. This is 0.0125 molarity. It splits up 1 to 1. Again, there is no H hooked up in there. So then, since this is a strong acid, 100%, it's going to be the negative log of 0.0125. The negative log of 0.0125 gets us 0.90, 1.90. Okay. So my pH is 1.90. So that makes my pOH equal to 12.10. Likewise, if I have a strong base, this is going to split up 100% into K plus. I should have put aqueous on there. And OH minus 100%. Now down here, we use the term with an acid, ionize. The base, we say it dissociates. 100%. Dissociates 100%. So if that splits up, every time I have 10 of these, I'm going to get 10 OH minuses, right? This molarity is just a number. You are going to have a concentration here of 0.0125 molarity OH minus. This ion here is going to be 0.0125 molarity as well. This would be labeled 0.0125 molarity KOH on the bottle, but none of those are going to be hooked together. This time right here, the pOH is going to be the negative log of 0.0125. Time the pOH is going to be 1.90. Be careful when the question asks whether or not you want pH or pOH. This is OH minus, so it's pOH, which makes my pH here equal to 12.10, or just the opposite. Okay. Let's do one stoichiometry problem on page 12. In fact, I've got this one down here labeled not so ugly owl, so let's do that. So that'll give you an idea. So not so ugly owl. Here's what it says. How many grams of potassium hydroxide right here will precipitate when excess sodium hydroxide solution is added to 53 milliliters of 0.72 molarity copper 2 sulfate? The nice thing about using molarity in milliliters is we get moles without grabbing the periodic table. It's faster and easier. My solution method is going to be exactly the same. This is going to give us moles. We're going to use the mole ratio fraction arrow to figure out moles here. And for this, it is 1-to-1, right? 1-to-1. How do I get moles here? This is a single unit number. Start with that. Put it in liters. How many liters? 0.053 liters of solution. Bring down my molarity as is. I'm not going to flip it. What does that big M mean? 0.572 mole per liter of solution. That gets me my starting moles right here, which is 0.03 to 368. Again, it's easier because you don't have to grab your periodic table. You're not looking up grams right now. But I got moles, same solution technique. Underneath the equation for moles, put your other stuff given on top. So I'm going to produce, it has excess sodium hydroxide. We do not have a limiting problem. I'm going to produce 0.0303 moles of copper 2 hydroxide. Now I'm just going to convert this. Now I got to grab my periodic table. You don't always have to grab your periodic table, but if you got grams, you do. So 1 mole of copper 2 hydroxide is grams. We could do this reaction in lab if we just filtered out copper 2 hydroxide. This would go through the filter paper. Molar mass there is, I believe, 97.57. So it looks like we would get 2.96 grams. This is an exact owl question. That's not very ugly at all. It's like, yes, I put not so ugly. So that's an example of some solution stoichiometry. Next time we meet, we'll for sure just finish up some stoichiometry and we'll start chapter 5. So print off chapter 5. Chapter 5's got some nice color to it. If you can get at a color printer, it would be nice. On your quiz, you can now go through on your quiz, you could try all of them. Especially do the pH ones, but look it over, just kind of scan it over. I don't know when this is due. This chapter 4, part 2, all is due when? I'll look. It's not for sure. It's for sure not by Tuesday. Right? So by Tuesday, we'll look at that deadline on that. So have a good weekend. It's going to be 80 degrees on Saturday. No, Sunday. Sunday is going to be 80 degrees. Enjoy your weekend.